Okay, today I want to cover the remaining part to the section 2.9, the dimensions and rank. So I didn't finish section 2.9 like yesterday, so I just covered the remaining part today. This is like the second part, the dimension of a subspace. What's that? The definition. The dimension of a non-zero subspace H is the number of vectors in any basis for H. It is the number of linear independent vectors in H. This is like a definition. The remarks. The dimension of a subspace H is denoted by dim H. Suppose H is the zero subspace, the dimension of H equals 0. We can write like this. The dimension of a column space of a matrix is the number of pivot columns, right? Here, the dimension of a column space, dimension of column space is what? The number of pivot columns. This is like idea. The dimension of a null space of matrix is the number of free variable in the solution to AX. So here, the dimension of a null space is the number of the free variables in a solution to AX equal to 0. So one more. Would you like a dimension R to N? Exactly N. The applying through 0 in R3 exactly 2 dimension. The line through 0 in R3 is 1 dimension. The 1 dimension. This is like the last lecture. We only review the last lecture. So now we can try to solve the one more problem. To find the dimension of a subspace H spanned by the vector, the V1, V2, and V3. So like this. So how can we solve? The main idea is here. The dimension of column space of a matrix is what? Number of pivot columns. This is whole idea. Number of pivot columns. So here, how can we solve? Like this. We can make the one matrix A by using the V1, V2, V3. So here, we can make matrix A. Matrix A is exactly vector V1, the vector V2, the vector V3. So what's that? This is same to 2, -8, 6, 3, -7, -1, -1, 6, -7. So we have this kind of things like this. The next tip. So you can change this one to the echelon form. I can change this in the echelon form. You have to keep 2, 3, -1, the next tip. This is like a first low, this is like a second low, this is like a third low. How can you eliminate -8? The second low here, we can use like a second low plus the 4 times first low. We can use it. So what happens? So we have it, second low is -8, the -2, and 6. The 4 times the first low, 4 times 2 is 8. 4 times 3 is 12. 4 times -1 is -4. And add it. So we have 0, 10, 2. So we have 0, 10, 2. Like this. The next one. Here, third low. We have the third low minus 3 times first low. Third low is 6. -1, -7. The 3 times, -3 times second low is, the 2 times -3 is -6. The 3 times negative 3 is negative 9. The negative 3 times minus 1 is positive 3, and add. So we have the like this. This is 3. So let me see. I made the one mistake. Sorry, this is like not negative 2. This is negative 7. This is my typo. This is negative 7. We have 5. Sorry, you can change 5 here. This is 5. So 5. The next you add 0, negative 10, minus 4. So we have 0, negative 10, minus 4. So next one, this is like a first row, this is second row, third row again. You can change it to the echelon form. You have to eliminate minus 10. You can keep 2, 3, minus 1, 0, 5, 2, 0. So next, you can change the third row. How can you do that? Here, third row plus 2 times second row. The third row is 0, the negative 10, and minus 4. The 2 times second row is 0, 10, 4. You add it. What's that? 0, 0, 0. So we have like this. So let me see. So how many pivots do we have here? 2 is a pivot, 5 pivot. So we have 2 pivots. 2 pivots. We have 2 pivots. So what's it like dimension of subspace H spanned by V1, V2, V3? Exactly. The dimension of H is number of pivot columns. We have 2. This is ideal solving this problem. Okay, this is like code idea. The next one here. Find the dimensions of a column space of matrix A. A contains 4 pivot columns. So what's it like dimension of a column space of A? The column space of A is exactly number of pivot columns. That's it, the 4. So we don't have more. The next, find the dimension of a null space of matrix A if the solution to AX equal to 0 contains 3 free variables. So what's that? We have the dimension of null space. The null space of A is number of free variables, 3. This is the final answer for solving this problem. The next one, what's like the rank of a matrix? The rank of a matrix is the dimension of a column space of A. So we can use this notation. The rank of a matrix A is denoted by rank A. What's it like a rank A? Rank of A is same to what? Dimension of column space of A. This is exactly definition of rank A. Rank A. The next, the rank of a matrix is equal to number of pivot columns of A. Is right. It's like previous, like the previous, like the material. So the rank of matrix A is equal to number of pivot columns. Here, this example, find the rank of the matrix A. How can you find the rank of matrix A? So this is the idea. You just only use the like this. You can change this one to echelon form. The same, change it to echelon form. So how can change this kind of things? The first row is like 3 is not good. I can change 1. You can the first row times 1/3. So we have 1, negative 2, 3, 0. The second row 2, minus 4, 7, 2. 3, negative 6, 6, negative 6. The next, you can change it. This is like first row, second row, and third row. I can change. You can keep first row. The 1, -2, 3, 0. The next, how can I eliminate the 2? The second row here. The second row plus -2 times first row. The second row is 2 minus 4, 7, 2. The -2 times the first row, -2 times 1 is -2. -2 times 2 is +4. -2 times 3 is -6. -2 times 0 is 0. And add 0, 0, 1, 2. The next one, 0, 0, 1, 2. So we have it. The next here, the third row plus the -3 times first row. We have 3, -6, 6, -6. We have 1. The -3 times the first row, -3. -3 times -2 is +6. -3 times 3 is -9. -3 times 0 is like 0. And add 0, 0, -3, -6. So we have 0, 0, -3, and -6. This one. The next, you can keep first row, 0, 0, 0, 1, 2. The next, you can eliminate -3 by using second row. This is like a first row, second row, third row. So exactly, you can calculate third row plus 3 times second row. So what happens? This is third row is 0, 0, -3, -6. The 3 times second row is 0, 0, 3, 6. You add it. We have 0, 0, 0, 0. So we have 0, 0, 0, 0. So next, you need to find number of pivot columns. We have one pivot here and another pivot. We have 2 pivot columns. 2 pivot columns. So what's it like rank A? The rank A is exactly same to the dimension of a column space of A is the same to number of pivot columns 2. So this is the final answer for solving this problem. It's good. The next, the rank theorem. If a matrix A has n columns, we have like n columns, then rank A plus dimension of null space equals n. So this is proof. Though we know the number of pivot columns in A is rank A. The number of free variables in A is dimension of null space from the previous slides. We have one note. The free variables are corresponding to non-pivot columns in A, right? Non-pivot columns in A. The number of non-pivot columns of A is exactly same to dimension of null space of A. The note. So we know this one. The number of pivot columns plus number of non-pivot columns is number of whole columns in A. So what happens? So exactly this one. The rank number of pivot columns is same to what? Rank A. You can replace. The number of non-pivot column is exactly dimension of null space, exactly same to the number of columns in A. What's that? N. So we have it. So always rank A plus dimension of null space of A is n. This is like a whole idea. This equation. Determine the rank of 6 times n matrix whose null space is 3 dimensions. So what's that? So we can use here. This is like a theorem, rank theorem. Was it like the dimension of null space? Null space has 3 dimensions, like 3 free variable. This is 3 plus rank A equals, so what is n? N is the number of columns of matrix A. Here, what's that? What is 6? This is rows. This is number of columns. So we have 8 is number of columns, like 8. You can subtract 3 from both sides. What is the answer? Is cancelled. Rank A. The rank of A is 5. That's it. This is the final answer for solving this problem. The next basis theorem. Let H be a p-dimensional subspace of Rn. Any linear independent set of exactly p element in H is automatically a basis for H. This is already true. So the H, dimension of H is always p. So we know here the dimension of subspace, the dimension of subspace of H is like p. So what's it like basis? This one. The linearly independent set of exactly p elements in H is automatically basis for H. Also, any set of p elements H, the span H is automatically a basis for H. This is always the same. So we have this one. Proof is very difficult, so we can use the next one. Use invertible matrix theorem, the isomorphism. So we didn't learn isomorphism, so only accept this result. Right. So, yep. So why this is true? So this is the invertible matrix theorem said p vectors in Rp are linearly independent if and only if they also span Rp. This is like you can use this kind of ideas. The p-dimensional subspace is also isomorphic to Rp. The inverse matrix theorem like continued. So what's that? Here, so let A be an n by n matrix. Then the following statements are each equivalent to the statement that A is an invertible matrix. So the columns of A forms a basis of Rn. The column space of A is exactly Rn. Dimension of a column space A is n. The rank A is n. The null space A is only 0. The dimension of a null space of A is exactly 0. This is like 0 is like vector. This is like a 0 vector. So here, the null space of A is like a 0 vector. The 0 vector. So we have it. The proof. So we can use this one, key, the inverse matrix theorem. Remember inverse matrix theorem here, section 2.3. So you are going to section 2.3, we can use inverse matrix theorem in section 2.3, the 2.3. So usually we can use this idea. So here, we can use this one. This is E. What's it like E? The E is the columns of A form a linear independent set, the equivalent to H. The columns of A span Rn. This is always equivalent. So this is also equivalent to the A is invertible matrix. The three kind of things. You can use the E and H first. So what's that? Here, this one. The columns of A form a linear independent set. The columns of A span R to N. So like this. The E and H equivalent to M, is right? The columns of A form a linear independent set. The columns of A span Rn. What does it mean? Here, exactly, the columns of A form a basis of Rn. This is like a definition of a basis of Rn. This is equivalent to. So next, you can use the another one like G. What's like G? G is here. AX equals B is a unique solution for each B in Rn. This is exactly equivalent to A is an inverter matrix, like this. We can use it, G. So here, the G, AX equals B has a unique solution for each B in Rn. So what does it mean? For any vector B in Rn, x1, a1 plus, x2, a2, till xn, an equals B for some x in Rn, where A is like matrix a1, a2, an. Right? This is exactly the unique solution. So this is exactly the equivalent to the column of A is Rn, is right? So we have the column of A is Rn, like this. So we have it. Was like dimensional column of N exactly same to this N, is right? This N. From the previous slides, the column, because here, dimension of a column of A is same to the dimension of like only Rn. Dimension of Rn is exactly this number N. This is already true. The next column of A is like N. Was like rank A is also N. This is definition. Was like a definition of rank A. The rank of A is exactly same to the dimension of a column of A. This is like a definition. So rank A is N. So automatically dimension of a null space equal to 0. Do you remember the rank theorem? The rank theorem is the rank of A plus the dimension of a null space of A equal to N. So in this case, rank N is N plus dimension of null space of A equal to N. You subtract N from both sides. So what happens? N is cancelled and cancelled. The dimension of a null space is exactly 0. So what does it mean? The null space is only here. This is like type of 0 vector. Only one 0 vector. That's it. The null space of A is 0 vector. The equation AX equal to 0 has only trivial solution. This is exact meaning, is right? So what is like a null space of A? Do you remember what is like a null space of A? The null space of A is you can collect all vector x such that the A times vector x is only 0 vector. So what's like a solution of x? The exactly 0 vector. We have only one trivial solution. This is like true. This meaning is exactly going back to G. AX equal to B has a unique solution for each B in Rn from here. Remember? Like D. The AX equal to 0 has only the trivial solution. The equivalent to AX equal to B has a unique solution for each B in Rn. So here, this is like true. The D implies G. So D and G, this whole thing is like equivalent to A is invertible, is right? Here, G is going to also G. What does it mean? D and G are equivalent. We are going back to here. What happens? G is going back to A. So A is invertible matrix by using the section 2.3. So this is true. So the proof is complete. Okay, this is like the whole idea for solving this kind of problems. So this is all for like today's lecture. So I hope that you just understand the section 2.9 like completely. So any question, any trouble, just send the email to me. I can help you. Okay, thank you for watching my video lecture.